All right, pretty frustrated. I just made this video almost to the end and realized that it quit recording at some point. I must have hit this little button in the upper right hand corner, so let's try this again here. We're talking about finding maxes and mins in R3, so local extrema in R3. It's really similar to what we did in Calc 1, but with a few exceptions here. So start with the definition here. Let f of xy be defined on some region R in the xy plane. All right, so this is just the domain. And let AB be some ordered pair in R. So 1. The function value f of AB is a local maximum if the value at AB is bigger than or equal to all the other values nearby. When we say nearby, we mean in some open disk centered at AB. Okay. So basically what it's saying is if you've got a curve out here and there's a max there and some little open disk around it, down here in R, here's AB. If you look at a little open disk around it, you look at all the values that the function finds, they're all going to be less than, they're going to be below the actual function value. And part 2 says f of AB is a local min if this value is less than or equal to f of xy in some open disk centered at AB. And so 3, if f of AB is less than or equal to f of xy for some points in this disk and greater than or equal to f of xy for other points in the disk, then f of AB is a saddle point. And these are the 3 kinds of extrema you can have. So you can have local maxes, local mins, and saddle points. And a saddle point is just something like if you've got part of the curve doing this, so you think, oh, I've got a minimum, but then another part of the curve goes down and around it. So it's got points that are, this is f of AB, you've got points above it within the disk and then also below it. So you get, literally it's a saddle. Okay. All right, so let's look at these maxes and mins here. So let's say I've got my axes here, and somewhere along in this surface, so this is the surface f of xy equals z. Let's say up here is a max, right? And sure enough, this has got some point AB that projects onto it. And we're assuming now that this is a max. So if you think about the partials or you think about the tangent plane, particularly the partials, at this point, the slope of the tangent line is 0, right? Because it's a horizontal tangent. And similarly, at this point, d partial dy is also 0, right? So it's a necessary condition at a max or a min that the partials equal 0, but that doesn't guarantee that it's a max or a min, which is exactly what we saw in Calc 1. Right, if you take some function like x cubed and you take its first derivative and set it equal to 0, you get a critical point, because f prime of 0 is 0, but it's neither a max nor a min, it's an inflection point. Okay. So here's the theorem. If f has a local max min at AB, then it must be that the partials at that point equals 0. But the converse isn't always true. It's not automatic that if the partials are 0 that it's a max or a min. This just gives us critical points, candidates for maxes and mins, right? Because the condition is necessary, but not sufficient to prove max mins. Okay. And also, if the partials are undefined, they could be a max or a min. Okay, so that's the theorem that tells us about critical points, right? So critical points happen when the partials equal 0 or undefined. And the actual working theorem to classify, it's they call it the second derivative test. Okay, so suppose the partials of f of x, y exist. Okay. 1. F has a local max at a point P naught if the second derivative is less than 0 and this number, the Hessian, which I'll show you in a second, is positive. Okay, so local max. So this is really saying it's concave down because it's negative, right? Okay, 2. F has a local min at P naught if the second partial is positive and the Hessian is positive, right? Concave up. And 3, if the Hessian is less than 0, then P naught is a saddle point. And 4, if the Hessian equals 0, the test is inconclusive. You got some more work to do, okay? And the Hessian is best written as the determinant of a 2x2 matrix of partials. And if you write this out, it's f of xx, f of yy minus, and since these are continuous functions, f of xy equals f of yx, so this is f of xy quantity squared. Okay, and so this number is the Hessian, and all we care about is its parity. Is it positive, negative, or 0? Okay. And so this is really straightforward, fun stuff. And then you look on GeoGebra and it all works out, so it's pretty satisfying. Am I still bloody? Yes. All right. Still recording. So 1. F of xy equals xy minus x squared minus y squared minus 2x minus 2y plus 4. Okay. And now if you think back to Calc 1, your first thing is to find critical points. So here we go. We take f sub x and set it equal to 0. And so whatever points we find have to satisfy both at the same time. So let's take the x partial. We get y minus 2x minus 2. We set that equal to 0. And then over here we take f sub y. We get x minus 2y minus 2 equals 0. And so this gives them a system of two equations and two unknowns. I put it into a matrix. I went 1, minus 2, minus 2, minus 2, 1, minus 2. I solved this, and I got 1, 0, 0, 1, minus 2, minus 2. And it says that our only critical point is the point negative 2, negative 2. Okay. So we've now created a list of one critical point. Okay. And now we want to compute the Hessian of f evaluated at minus 2, 2. Let's do this in two parts. So what's f sub double x is negative 2. F sub xy is 1, 1. And then f sub yy is negative 2. So this gives us 3, which is greater than 0. So that puts us, it's either a max or a min. F of xx is minus 2, which is less than 0. So when you go up here and you go, okay, f of x is less than 0, so it's by part 1 of the theorem of a local max. F of minus 2 is a local max. And if you really wanted to finish this, it's minus 2, 8. That's the point. Okay, it's still recording. So let me, let's see if we can't. Pull up our old friend here. Okay, so we're going to input go to here, xy minus x squared minus y squared minus 2x minus 2y plus 4. Okay. And let's put in the point minus 2, minus 2. Oops. Minus 2, comma 8. And there it is. Let's make this bigger here, right? You see right there at the top at minus 2, 8, there is a local maximum. Okay, well, now I've been on this video forever because I've made it already once, so I'm going to leave the second problem I did before for you. So this is get bigger here, come on. So this is going to be that's why. This is going to be guided practice, okay? And we'll start class by going over this. So you're to find the relative extrema of the function f of xy equals 3y squared minus 2y cubed minus 3x squared plus 6xy. And we'll start class with this. See ya soon.